Welcome everyone to our seminar today. So our speaker today is Dan-Virgil Voiculescu from UC Berkeley. So he's going to tell us about around the quasi-central modulus. So please.
Should push continue, yeah. So I'd like to thank the organizers for the invitation. It is so nice to speak in this seminar online and to see so many people online. So there is a big difference between perturbations of Hermitian operators in finite dimension and in infinite dimension. In finite dimension, the difference between two Hermitian operators may be as small as you want, and still nothing of the structure of the Hermitian operator is preserved. Everything changes, the eigenvalues change, there is nothing preserved in finite dimension. In infinite dimension, this is not so. If the perturbation is small in a suitable sense, then a part of the spectral structure is preserved. That's the difference from finite dimension and infinite dimension. And this has to do with the fact that the algebra of bounded operators on a finite dimensional Hilbert space is simple, while in infinite dimension, this algebra has non-trivial ideals. These ideals include in particular the normed ideals, and these are the ideals to which Alain Kohn has assigned the role of infinitesimals in non-commutative geometry, the normed ideals. So I'll start with recalling a few things about normed ideals. So it's an ideal of compact operators or among the bounded, in the algebra of all bounded operators on a Hilbert space. I'm not going to give all conditions, but one key thing is that besides the uniform norm, there is this second norm. So there is I, and there is this other norm, norm index I. And we have this key property that AXB, where X is in the ideal and AB are bounded operators, is bounded by the norm of A, the uniform norm of A, uniform norm of B, and in the middle, the special I norm of X. And I'd like to give a few examples which will play an important role in what I have to say. So let's denote this Sk of T, the so-called kth S number of T. These are eigenvalues of the absolute value of T. It can be characterized also in the following minimax way. You take T and restrict it to a subspace of codimension K, a closed subspace of codimension K, and then you take the norm of this. And you take the inf of these norms when restricted to such subspaces of codimension K. And then the norm is of the following type. The I norm is a certain function with some nice properties and depends only on this sequence, S1 of X, S2 of X, the sequence of S number. These are the eigenvalues, if you want, of T star T square root. And among these, there are the Schatten von Neumann classes, the CP normed ideals with the P norm. The P norm X of X is the sum of these S numbers to the power P. It's a little LP norm of the sequence SK. And then among these, for me, the Lorentz P,1 ideals will play a very important role. So there is this Lorentz scale with two indices P, Q. The Lorentz P, Q are increasing in Q, and the Schatten von Neumann class is the class P, P. And you have here a lexicographic order among these ideals. Yeah. So somehow the second index is a refinement of what you have around P. And I got used to denote this P,1 ideal by C minus P. And here is C minus P norm. The C minus P norm is K to the power minus 1 plus 1 over P, Sk of X, the kth number. Well, this is an ideal which is smaller than the CP, than the Schatten von Neumann class. If P equal 1, it is equal to the trace class, but otherwise it is smaller. You get an idea of what this norm really is by thinking of the by thinking in the following way. It is somehow the largest norm, which is the P norm on projections. So if you take that projection of dimension K has norm K to the power 1 over P, then this is somehow the largest norm which has this value on projections. And these ideals will turn out to be actually more important for me than the Schatten von Neumann ideas. Okay, so here are, I'll start with some of my older results on perturbations of N-Tuples of commuting self-adjoint operators. So if you have two N-Tuples, alpha and beta, of commuting self-adjoint operators, so AI, AJ equals AJ, AI, and they are self-adjoint, and you have beta, and the difference is AJ minus beta J are in a normed ideal. That would be I perturbation of an N-tuple of commuting self-adjoint operator. So I assume that the perturbation gives again a commuting N-tuple. It's from commuting N-tuples to commuting N-tuples. Then, if the normed ideal is C minus N, this N,1 class, then the Lebesgue absolutely continuous part of the spectrum of the operator is preserved. So you look at the spectral measure. The spectral measure is projection valued measure, but also you can decompose it into a part which is Lebesgue absolutely continuous and a part which is singular, and then you take the restriction to the absolutely continuous part of the spectral measure, and this is the absolutely continuous part of the N-tuple. So if the perturbation is in C n,1, or as I denoted C minus n, then the Lebesgue absolutely continuous parts of the two N-tuples are unitarily equivalent. So this is preserved by such perturbation. This is where the difference appears when you take perturbations which are small in the sense of being in normed ideals. Now, if one goes beyond the C minus n, then what happens is that alpha and beta can be mutually singular. So they may have, their spectral measures may be mutually singular. So if n equal 1, the first result is a classical Kato-Rosenblum theorem. And the second one is the classical Weil von Neumann-Kuroda theorem. So Weil von Neumann, that's compact, the I is compact, then is C2, and Kuroda is all the I's which are larger than C minus N. Now, I have generalized these things when N is larger than or equal to, using a different technique, on part for the Weil von Neumann part, so the second assertion, this thing, I used an adaptation of my theorem, an adaptation where instead of compact operators, one puts normed ideals. And in all of these, a key role is played by the quasi-central modulus. The quasi-central modulus, it's an invariant number which is associated with an N-tuple of commuting, not commuting, excuse me, a general N-tuple of bounded operators and a normed ideal. I will mostly make these N operators to be self-adjoint, but it's not key that they be commuting. However, in the talk I'm giving today, I will talk mostly about the results which have to do with commuting self-adjoint operators. So here is about the quasi-central modulus, what kind of object it is. So it's first a notation. It's K. There is an index I, which is the normed ideal, and tau, which is the N-tuple of bounded self-adjoint operators, but they are not necessarily commuting. So K sub I of tau is a number which is associated with a normed ideal I and this N-tuple of operators. And it is the smallest number, as a definition, it is the smallest number between 0 and infinity for which there exists an increasing sequence of finite rank operators, AM, finite rank positive contractions, so they are positive operators between 0 and 1, and they increase to 1, such that if I take the maximum of these commutator norms, I norms, so I'm taking all the commutators of AM with the TJs, yeah? And I'm taking the max of these I norms. Then as M increases, this has as a limit C. C can be also infinity, can be 0, yeah? C is a number in the interval 0, infinity, yeah? So again, Ki of tau is the limit, is the smallest possible limit of such commutators norms of AMs, of finite rank positive contractions with N-tuple. And I'm going to use, in two particular cases, specific notation. So if the ideal is a Schatten von Neumann class, this will be denoted by Kp of tau. And if the ideal is this C minus P, this P, 1 Lorentz ideal, then the notation will be K minus P of tau. And here are the general properties of this K minus P of tau. I'm formulating them for these C minus P ideals. They are more general, they are for general normed ideals, but it is nice to see them on the scale of C minus P ideals. First of all, from P, from the number P, to K, so the tau is fixed now. From P to K minus P of tau, I have a decreasing function of P. That's the first property. Then, if there is a number P0, no, excuse me, there is always a number P0 between 1 and infinity, so that to the left of P0, so below P0, K minus P of tau is infinity, and above P0, it is 0. So in particular, if I would have k minus p of k minus p for a certain p of tau be finite, then I know that above this I'm going to have infinity, finite and non-zero. Above this I'm going to have plus infinity, and below this I'm going to have zero. So there is always such a p0, such that below p0, k minus p is infinite, and above p0, this number is zero. Now, the number kp of tau is not very interesting. And this is said by the next property, namely, if p is larger than 1, then this kp of tau takes only the values 0 and infinity. If p is 1, then it's the same thing as k minus 1. And then there are interesting things. Another property is that it is an invariant under perturbations from the ideal I, under the condition that the ideal I would be one of the ideals where the finite rank operators are dense. Yeah, this is one of the subtleties of norms of normed ideals. So in particular, the C minus P or the CP are such ideals. So if tau and tau prime differ by something in the ideal I, then this Ki of tau must be equal. Ki of tau and Ki of tau prime must be equal. And then there is, so you see, the definition can be used to get upper bounds on Ki of tau, because it is the least number you get as a limit of such norms of commutators. But how does one get lower bounds? Lower bounds arise from what I've written here as property 5. So Ki of tau is larger than 0 if and only if there are self-adjoint elements in the dual of the ideal, so Yj equals Yj star, such that the trace of I times the sum of the commutators of Tj's with Yj is a positive operator, which is in, excuse me, is an operator with positive trace. So this, as I've written here, is a Hermitian operator. So if its trace, this trace of the sum of commutators is strictly positive, then the Ki of tau is larger than 0. One has to have that this sum here should be in C1 plus positive operators, yeah, plus all positive operators, because I need to have also the possibility that this trace should be plus infinity. And so it's going beyond C1, and it's C1 extended with B of H plus. So you see, if to get lower bounds on Ki of tau can be difficult. It requires to find such Yj's for such that such a sum of commutators have positive trace. And in many situations, this is achieved by considering certain singular integrals. For instance, in the case of one Hermitian operator, it is the Hilbert transform, which plays this role of Y, but in other cases, there can be more complicated singular integrals. And now there is a nice formula in the case of N-Tuples of commuting self-adjoint operators. It is this, that this number K minus N of tau, if I raise it to the nth power, is equal to a constant gamma n, a universal constant gamma n, which is finite and strictly positive, of the integral with respect to Lebesgue measure of the multiplicity function of the n-tuple tau. Yeah. So I have an n-tuple tau of commuting self-adjoint operators. They have a spectral measure. The spectral measure has a multiplicity function. And then the integral of the multiplicity function with respect to Lebesgue measure is proportional to K minus N of tau to the power N. So as you can see here, actually only the part of the absolute of the multiplicity function for the Lebesgue absolutely continuous part enters, because the rest is where the multiplicity function on the singular part, but this has the Lebesgue measure 0. And this formula has found technical use in Alain Cohn's work on the spectral characterization of manifolds, this formula. And what I want to talk today about is two recent generalizations. One to the hybrid case, and the other to the fractal case. I'm going to explain what this means. So first, the fractal case. What does it mean to take this theory to the fractal case? Well, say I have two. It means to replace Rn by a fractal set. So instead of Rn, I'm going to consider a fractal set X, and I'm going to, my results are for fractal sets of the simplest kind, because these are early results, it's the beginning only. So I'm having alpha and beta, two N-Tuples of commuting self-adjoint operators. And then, you know, usually you have the spectrum of these two is contained in Rn. Now I'm replacing Rn with a fractal set. So I'm having these two N-Tuples, alpha and beta, and their spectra are contained in this fractal set X. And then I'm having the differences, the alpha j minus beta j, bj, are in a certain normed ideal I. Now, Lebesgue measure on Rn, for the fractal I have chosen, there is a replacement which is the unique self-similar measure on this Cantor-like fractal sets. It's so-called Hutchinson measure. And in the case of the fractal, I consider it is the Hausdorff P measure, actually. So this self-similar measure is the Hausdorff measure. And when there are not Lebesgue absolutely continuous part, there are Hutchinson measure absolutely continuous part. So these are sets where self-similar sets which are defined by self-similarities of the simplest type. They simply, it's simply multiplication by a constant which is between 0 and 1 and the shift. That's are the self-similarities I consider. And besides, I arrange that the set should be Cantor-like, should be totally disconnected. This should work also with minor adjustments, for instance, for things like the Sierpinski gasket, where you have to remove a sequence of points and things like that. So here is what I was able to prove. First of all, one has all these results that the absolutely continuous parts are preserved if the ideal is C minus P. Now here P is the Hausdorff measure of the self-similar fractal set. So, and the absolutely continuous part, as I said, are with respect to the Hutchinson measure. So if the perturbation is in C minus P, then the absolutely continuous parts are unitarily equivalent. This follows from all the results I had that you have such things. But here comes the new part. The new part is that the formula can be generalized, the formula for K minus P. So if tau is an N-tuple of commuting self-adjoint operators, the spectrum is in this fractal set, then K minus P of tau to the power P is a universal constant depending on X, gamma X, and it is the integral of the multiplicity function with respect to the Hutchinson measure, which is here as a Hausdorff P measure. So it is exactly like the other formula, only that instead of dimension n, you put this fractional dimension p, and the integral is not with respect to Lebesgue measure, but is with respect to Hausdorff p measure. So what are the ingredients for this result? On one side, one has to prove that this constant gamma is positive, is strictly positive. So I have to have a lower bound. And there, the work I had done time ago with Guy David on S numbers for certain kernels, this is the relevant thing. But, and this is a relevant thing also for the preservation of the absolutely continuous parts, etc. But the fact that you have an exact formula, this is due to the following thing of which, about which I became aware only now. It is that this number k minus p for any n-tuple of bounded operators has a general ampliation homogeneity property. So k minus p, if I take the tau and I tensor it by in, so if I take ampliate by n, then the k minus p of tau gets multiplied by n to the power 1 over p. Such a property is obvious if you have kp, if you have the Schatten von Neumann ideas. It is quite trivial there. Here it's non-trivial that you have such a property for these p, 1 ideals. And I was aware of this for p equal 1, where it's the same thing as Schatten von Neumann class, and I was aware of this for p equal infinity, but so where there is no n 1 over p, because 1 over infinity is 0. But it's been a surprise for me that it's true also for the other p and with k minus p. So this is the source that there is such a formula in fractional dimension. Now, about hybrid perturbations. Hybrid is another situation where I'm having alpha and beta, two n-tuples of commuting self-adjoint operators. And now the perturbation is not in a particular ideal the same all the time. Namely, there is for each index j, there is a different ideal. So I'm having alpha j, aj minus bj is an ideal I sub j, where j varies with the index, ij varies with the index j. And then, of course, I have this k, this quasi-central modulus, which depends not, it's not k sub I of tau, it's k sub I1 In of tau. And it's again the smallest number c, which you get as a limit of maximums of commutators, commutator norms of AM Tj. But you take every time the commutator norm in a different ideal ij. So it's the same definition with this change. Instead of here norm I norm of AMTJ, you have IJ norm of AMTJ. The limits you get. And this number I denote, if I take Schatten classes, I denoted Kp1 Pn of tau. Otherwise, I denoted K minus P1 Pn of tau if I'm taking this C minus P ideals. Now, instead of looking at P, I'm going to, instead of looking at 1 over n, I'm looking now at 1 over P1 plus 1 over Pn equal 1. So the results I had for n-tuples of commuting self-adjoint operators with Lebesgue measure, etc., they work more generally if I have such hybrid perturbations, and the aj minus, so the jth perturbation is in the ideal C minus pj, where this the reciprocals of the pj's have some 1. So 1 over p1 plus 1 over pn gives 1. Yeah. Then I have similar results. I have, for instance, that the Lebesgue absolutely continuous parts are preserved. If I go beyond, in a certain sense, these ideals, again, the spectral structure is destroyed. In particular, I have diagonalizations, whatever you want. The nice thing is that also in this situation, the formula holds, the formula for the number k for the quasi-central modulus holds. So I'm having k minus p1 pn of tau to the power n is a universal constant, gamma, which is non-zero, of the integral of the multiplicity function with respect to Lebesgue measure. It is the same formula, and it holds also in the hybrid case. Now, what is the technical part of this? Well, many things can be adapted easily, but there is a difficulty, and a serious one, is improving that this universal constant gamma is strictly positive. That's where the work goes. And it is, so if you have a Kato-Rosenblum n equal 1, you deal with the Hilbert transform, and you have to deal with the boundedness of the Hilbert transform. If you go for n, you had to deal with some other singular integrals of kind of these things. So if you have fractional dimension, you had these things of Guy David, from this paper of Guy David and myself. Now here, you have to use singular integrals of mixed homogeneity. That's the difficulty. They are mixed homogeneity. Yeah, it's a different, and there are a number of additional difficulties to prove that this number gamma is positive. Okay, now I'd like to discuss another topic. I've been and I'm still am trying to understand why this quasi-central modulus works so well in perturbation questions. And I've been trying to find structure. I mean, when we try to understand why something works, we usually think there is more structure around that quantity. So I introduced some algebras, and which should tell us more about this quasi-central modulus. They are the commutants mod normed ideals. So I'm having, again, an N-tuple tau of Hermitian operators, bounded Hermitian operators, Tj, of Tj star. And I'm having I, a normed ideal with this I norm. And now I look at the commutant of tau modulo I. So I'm looking at all the bounded operators such that these commutators X with Tj are in I. Then the natural norm on such an algebra is to put the sum of the uniform norm plus the max of these norms, of these I norms of commutators X, Tj. And this is a Banach star algebra, this ETI. That's a commutant mod I of the N-tuple. And what turned out? It turned out that to understand these algebras, one has to consider the ideal of compact operators inside. So it's the intersection of E tau I with the compact operators. This is the compact ideal. And then there is a Kalkin algebra for this situation. It is the quotient of the commutant by the compact ideal. And of course, I mean, if you take, for instance, the N-tuple tau to be a scalar or so, you get the usual Kalkin algebra, the usual compact operators, things like that. Now, what is the connection between the quasi-central modulus and this commutant. It has to do with approximate units of the compact ideal of the commutant. I mean, the full commutant in this full commutant mod the norm the ideal is a kind of double centralizer of the compact ideal. And what you have here, you have this ideal k tau I, where all the structures comes from, and k, the quasi-central modulus, has to do with approximate units. Now, the quasi-central modulus, what is interesting about this, except exact values, is whether it is 0, whether it is infinity, or whether it is finite and non-zero. And here the connection is the following. The quasi-central modulus of tau, mod the ideal I, is 0 if and only if this k tau I, capital K, so if and only if the compact ideal in the commutant mod I has norm 1 approximate unit. If and only if there is an approximate unit which is contractive. Contractive in this free norm. I've written here exactly what it means, but this is the equivalence. The quasi-central modulus vanishes. This ideal has a norm 1 approximate unit. The ideal is fine. The quasi-central modulus is finite if and only if this ideal has a bounded approximate unit. And of course, if there is no bounded approximate unit, the quasi-central modulus is infinity. The connection between quasi-central modulus and approximate and the norm of the approximate unit is not so good, but it is monotonous if you want, but it's not so good, it's not so nice. In any case, but from the qualitative point of view, this is the connection. Quasi-central modulus, approximate units. And then there are other properties. You see, if this quasi-central modulus is 0, then the Calkin algebra of the commutant is a C-star algebra. And it is a C-star algebra isometrically. Namely, you take on this quotient Banach algebra, the quotient Banach algebra norm, and you get a C-star algebra. So this commutant looks in many situations like this. You have a separable ideal here, this ideal of compact operators. You have, it's not always, but in good situation, it is separable. And then you have this big Calkin algebra, which is a C-star algebra, actually, if the quasi-central modulus is 0. Also, this quotient is a C-star algebra, but not with respect to the same norm. Its norm is equivalent to a C-star algebra norm if the quasi-central modulus is finite. In particular, if you take this ideal C minus infinity, then this C minus, that's an ideal which is in duality with the ideal on which the Dix-Viet trace lives. Then it's Matsayev dual ideal. Then you always have it's always isomorphic to a C-star algebra. That's what happens for all N-Tuples of operators. Okay, now I'd like to speak about some other development around these questions. I mean, it's around considering commutants, mod normed ideals. It is quite natural, of course, to look for, to generalize this object from N-Tuples of commuting operators to manifolds, to smooth manifolds. And so one can look at commutants mod for differentiable manifolds. So X will be a smooth compact manifold with boundary. I don't want to bother you with the boundary. I'm going to think all the time that it's a smooth compact manifold. And of course, on such a manifold, you have a measure, newer measure, which is equivalent to Lebesgue measure in local parameterizations. Then you have, independently of what particular measure you choose, you have the L infinity algebra, and every function gives multiplication operator MF. Every such L infinity function gives a bounded multiplication operator in L2 of x mu. And if I have now a normed ideal I, and I'm going to put this technical assumption that it is that the finite rank operators are dense. Then I can associate an algebra in the following way, a commutant in the following way. I'm taking an embedding of x into Rm. In the case I have boundary, there is this condition, neat embedding you, but I'm not going to bother you with this. So you take any embedding of x into some Rm, and then what you do is you take the commutant of you take the commutant of all multiplication operators by C infinity functions. Here we should have put an additional parenthesis, yeah? The C infinity functions with x. X is in the L2 space of x mu, which are in I. So you take all, but this is equivalent to being the commutant for the functions, to being in the commutant mod I for the functions which give you the embedding, yeah? So if you take an embedding produces an M-tuple of C infinity functions, and then the commutant of the multiplication operators with respect to the C infinity function, the commutant mod the ideal I, is the same thing as the commutant mod I of this, which is now the whole algebra of C infinity functions, yeah? So it becomes an object which is attached to a manifold, yeah, this compact manifold EXI, and it depends, this algebra up to unitary equivalence depends only on X and on I, and if I change these embeddings, I'm getting equivalent free norms, and what you have that the group of diffeomorphisms, of X acts by automorphisms on this commutant, on this EXI. So having the manifold X and the ideal I, and then up to unitary equivalence, there is associated this commutant mod I, and the diffeomorphisms act as automorphisms of this algebra. And then I'm having also a compact ideal. It's the intersection of this algebra with the compact operators. I'm having a Calkin algebra, again, the quotient of the commutant mod I with the compact operators. And this call it the Calkin algebra of EXI. And here are the properties of this Calkin algebra E over K xi. So I'm looking at the Calkin algebra. And the ideal I will be one which contains C minus n. N is the dimension of X. And the ideal can be equal to this C minus n. So that's the Lorentz n,1 ideal. So there are certain results I have when the ideal is equal to C minus n, and some which are when I'm going from C minus n beyond, yeah? So there are situations when I is strictly bigger than C minus n. There are situations when it's all possible i's from C minus n on, and there are things about C minus n. But I must say I've been mostly interested in what happens when I is equal to C minus n, because there are these things about preservation of Lebesgue absolutely continuous parts. So first of all, in all these situations, the Calkin algebra is a C-star algebra. You have it is a C-star algebra. If I is strictly larger than C minus n, it's isometrically a C-star algebra. Otherwise, the norm is equivalent to a C-star algebra norm. The second thing is about the center of this algebra. The center is the continuous functions on the manifold X. So you take the multiplication operators by continuous functions on X, they are act in L2 of X with respect to that measure mu, and when they become operators in these elements in this Calkin algebra, and it is the center of this Calkin algebra. Now, there are other properties, namely that which have to do with the preservation of Lebesgue absolutely continuous parts. Here the results are, so the ideal is C minus n, and n is larger than or equal 3. So from dimension 3 on, if I take a sequence Vm of C infinity functions, which are of absolute value 1 all the time, yeah? So it's functions from X into the unit circle. And I'm looking at the multiplication operators by this Vm, and I assume that their weak limit as m goes to infinity is 0. So imagine something like that. For instance, these Vms start oscillating faster and faster. When these multiplication operators, their weak limit is 0. Then the first result, which is a type of, it's kind of the generalizations I had for the Kato-Rosenblum theorem, is that the strong limit of conjugating T, any operator in the commutant modi, by these multiplication operators by Vm, yeah? So these are unitary operators, this M, Vm, T, M, Vm star. The strong limit exists for every T. These are generalizations of the wave operators, yeah? These are generalizations of the so-called generalized wave operators. And there is one difference from what you know from Kato-Rosenblum. The limit is the same all the time. There are, in dimension 1, you have 2 wave operators. Here there is just one. It is always the same. And it does not depend on the choice of the Vm. You realize once you prove such a theorem that you have such a limit, you can take 2 sequences of Vm, mix them, and the result gives you that the result does not depend on the sequence. Okay, now what does this give about the Calkin algebra? It gives us that the Calkin algebra, there is a homomorph, so this phi, this map phi, gives us for the algebra E a homomorphism into the L infinity algebra on X mu, is a star homomorphism, and this vanishes on the compact operator. So we're having actually from the Calkin algebra of X a map, a homomorphism to the image in the Calkin algebra of the L infinity function. So there is such a basic homomorphism which you have all the time from this into the Calkin algebra. And okay. And so what are the K-theory consequences of these facts about the Calkin algebra you get for a manifold X with boundary and an ideal I? First of all, the fact that the continuous functions are in the center makes this Calkin algebra a C of X algebra. It is a C of X algebra, and the K-theory of C of X acts on the K-theory of the Calkin algebra. But there is a warning here. It is that this is not the algebra of a continuous of a field of a continuous field of C-star algebra. This is not. It is much more discontinuous than what you are used with C of X algebras. Many of the C of X algebras one considers are algebras of continuous fields of C-star algebras. This is not here. This is much more discontinuous, but it is still a C of X algebra. And the second thing is that if n is larger than or equal 3, then the K-theory of L infinity of X, yeah, this for Neumann algebra. So the K-theory of L infinity, that's the bounded function, essentially bounded functions with values in the integers, yeah, that this group, that's K0, is a direct summand in the K-theory of the Calkin algebra. So if n is larger than or equal 3, the K-theory of L infinity is a direct summand in the K-theory of the Calkin algebra. But this shows another thing. So first of all, it is not coming from a continuous field of C-star algebra, but results like this also show that the K-theory of these manifolds is not homotopy invariant. You don't have homotopy invariance here. You have these K0s, which are not homotopy invariant objects. Because you can take a disk, for instance, which is contractible, and you still get something, and instead of getting 0, as you would get if it's homotopy, or getting the Z or things like that, it's not homotopy invariant. Now, because it's not homotopy invariant, etc., one would dream at least to see at least how one can simplify matters to. So there is this mystery what actually these groups are, and one would like to reduce things, if possible, to things like disks or toruses or things like that, simple things, and have the mystery at least in this K-theory of disks or so. And the good thing is that because one has this C of X algebra fact of if the continuous functions are in the center, one can have Meyer-Vietoris type sequences for connected sums. So if I take two such manifolds, X and Y, and I'm taking an ideal J, which contains the C minus n, so from C minus n on, it could be C minus n, but it can be larger. And I'm taking the connected sum of two such manifolds. Then the Meyer-Vietoris exact sequence can be adapted to this situation. And one gets this type of Meyer-Vietoris. I mean, you see it's a K star here in order to write just a triangle and not to have a 6-term sequence. You see also this, here there is not Y, there is Y, and there is also Y with a point removed and things like that. What does it mean? If I have here, instead of the manifold, I write the manifold and an open set here in the manifold, then it means I'm simply considering in this commutant the ideal which is generated by the functions. They have all these continuous functions, they are multiplication operators, continuous function with support in the open set. This gives an ideal, and so this is a certain C-star algebra. And I'm having this Meyer-Vietoris sequence. So somehow Meyer-Vietoris does not solve everything for going over from disks to more general things. But it shows that the main difficulty for understanding these things well is mainly disks and things like that. It's kind of differentiable structure problem. So I'd like to conclude the presentation with a problem. I've chosen what is perhaps the simplest problem, the simplest situation where I know absolutely nothing, and I think it's good to start on certain things, to start with the simplest things. Simplest, I'm not sure it's what to say about what the answer might be. So if I take the manifold to be 0, 1, the interval 0, 1, and I'm taking the K0 of the commutant for 0, 1, yeah? What is this? I think you have L2 of 0, 1 with respect to Lebesgue measure, and you take the multiplication operator by the coordinate function, and then you take the commutant mod trace class of this multiplication operator. Then I know that K0 is the same thing as K0 of L infinity, of the L infinity algebra. So K0 is exactly the Lebesgue, is exactly modulo sets of measure of Lebesgue measure 0, the measurable functions with integer values which are also bounded. But I have no idea about K1. I don't know whether K1 is equal to, it vanishes like it would be for the von Neumann algebra. I don't know whether it's bigger. I have absolutely no idea. I have formulated in one of my papers an example where I don't know how to determine whether it gives a K1 class which is trivial or not trivial. All these K1 questions seems to have to do with refined this refined trace class scattering theory, and probably somebody who is an expert on that may find the answer to that. I really don't know what K1 in this one-dimensional case is. And now about references. So I had a survey where you can find many of the things which has appeared in the volume for Alain Comte's 70th birthday. It contains most of the things, recent things, but not these things with the fractals and the manifolds. That's more recent. So you have here the survey and also connections to an earlier survey and other things. And here there are few preprints. This one is some results on a K-theory problem about threshold commutants and normed ideas. This is where the K1 problem is formulated. This other one, number 3, is the formula for the quasi-central modulus. Is in the fractal case. And here is the stuff with manifolds, with the differential things, and there are also other topics I've discussed here in this miscellaneous book. So thank you for your attention. That's what I had to say.
Thank you.
Thank you.
Any questions or comments?
Yes, well, I just want to ask, Dan, when you identify the K0 with L infinity, can you give a simple explanation of how you associate to a measurable subset the element in K0, I mean the projection?
So what are the K0 elements?
Yes, yeah, that's my question.
It has to do with projections. One can, like for C-star algebras, the projections, you may get them to be orthogonal projections. That projections in this commutant. Now, what is a projection in this commutant? The projections in the commutant of one Hermitian operator, you have on this space, you have also the compression of the Hermitian operator.
So you mean something like the Hilbert transform would help to do that? Or?
No, I'm having a projection in this commutant. And I'm having the Hermitian operator which defines the commutant. Then I'm taking this Hermitian operator and I'm compressing it to the projection.
Oh, that's it. I see.
That's a new Hermitian operator, and it has a multiplicity function. And the fact that the multiplicity function, that it's Lebesgue absolutely continuous part is what matters. That is, so this result is an application of Kato-Rosenblum.
I see.
Kato-Rosenblum gives you that you have this isomorphism of the K theory. So somehow Kato-Rosenblum means it becomes a K theoretic, as a K theoretic reflection here.
I understand. And then to do it for K1, you would need to do that with parameters somehow, with an S1.
I don't know. For K1, I really don't. I really don't know what it means. I have an examples of something in a Kalkin algebra there, which I'd like to perturb and see if I can contract it, and I don't know how to do it really.
Well, maybe you can find a cyclic cocycle which pairs non-trivially with it or something.
No, I mean, cyclic cocycles, they are useful in what happens in dimension 2.
Yes, I understand.
So there is this question of homotopy invariance which fails. So it fails if you have the ideal C minus n. But if you are in dimension 2, I know that homotopy invariance of K0 will fail. Also, if you take the ideal C2, also if you take Hilbert-Schmidt, so you have diagonalization mode mode C2, but it fails, and it fails for a cocycle reason. It has to do with the Pincus functions, Helton-Howe formula, things like that, which has to do with the cocycle. But I don't know more.
But is it right to think, I mean, in a very vague way, of the construction as some kind of quantized differential forms that you are doing, and which are sort of, you know, it's a kind of, I mean, if it were local, but.
I don't know. There may be, I don't know. I mean, I don't know whether these commutants, I mean, in many situations, one has things basically like pseudo-differential operators and things like that. Here, I don't know exactly what to get. It's a bigger thing of kernels. It's something can be huge. In any case, it would include things like pseudo-differential operators with L infinity coefficients and things like that, and it can be much bigger. I don't know what it is. I don't know what it is. In any case, it's a natural object from the perturbation point of view to ask what these objects are.
Any more questions or comments? Can I ask a question then? So for your manifold, you include boundaries. So is it, I mean, if we consider closed manifold without the boundaries, does the story become simpler or more complicated?
I think it's about the same, but I need it. I really wanted to do these things in the simplest case, but I needed the boundary to get these connected sums, to deal with the connected sums and have enough space to make construction. That's otherwise I would have stayed with closed manifolds. And
Yeah, so the question is, for example, for your problem, so do you know anything about the circle?
I know in my paper, this paper 2, I deal with the circle. And the circle is a little more complicated because one has also, the K-theory also has a projection can give rise to an index. Yeah, you have projections which commute with a modulo trace class with a multiplication operator, and the compression of the multiplication operator has an index. So you must take also this index into account. So it becomes, but otherwise it's not too different from what we had for the intervals.
Okay, thank you. So if there's no more question, let's thank our speaker again for a beautiful talk.
And thank you for the opportunity of
Yes.
being here and of meeting.
Thank you, Dan. Thank you.
Thank you again for attending our seminar today. So everyone has a nice weekend, and
Yes.
see you next
Thank
week.
you. Bye.
Okay, thank you.
Bye. Thank you.
Bye-bye.